All right, so welcome to Math 140 Calc 2. This is lecture 18. And what I want to do today is I want to talk about sequences and series. The most important one for us is going to be the geometric series and the geometric series formula, which you've seen. Talk a little bit about convergence tests. What is the difference between the necessary and a sufficient condition? And I've been really thinking about how do I want to do this, because this is a topic that's been done to death many, many times. And I thought I would come up with a slightly different motivation for why we want to do all of this stuff on sequences and series and convergence and all that. And I'm going to try to motivate it through mathematics as an experimental science. And again, the actual results that we're going to, you may never use in the rest of your life. But I'm trying to use this as a springboard to talk to you about how to think, how to attack new problems, how to gather data and analyze. If you were to have supreme power over the universe, and it is up to you to design the laws of calculus, what would you design the derivative of a product to be? Product of the derivatives, right? We all agree that if we had supreme power, this is what we would do. We'd make the lives of calculus students easy. And we'd get rid of the QWERTY keyboard as we were talking about earlier today. But we'll focus on just the math right now. So you want priorities. First priority is calculus, and after that, then you do the mechanics to write up calculus. Although everything is not auto-assist. So let's try to conjecture. Oops. Plug in all three cables. I only plug in two out of three cables. Right, so the product rule. The derivative of fg is f prime of x g of x plus f of x g prime of x. We can prove this. And the way we prove this is we add zero in a clever way. Does anybody remember how we motivated it? What did we do to build up evidence in favor? Does anybody remember? I think we did that. This in this case. So what functions did we look at to try to build evidence for this? Did evidence from f of x equals this, g of x equals this, f of x, g of x. I needed two functions such that I could differentiate them and I could differentiate the product. We could do x and x, but we could do it more generally. Rather than x to the first power, what could we do? We could do x to the n, x to the m, and then x to the n plus m. And if we did that, it actually worked out. And we believe that the fg prime should be a function of f, g, f prime, and g prime. It makes sense that the derivative of the product should somehow involve these quantities. We can take special cases of g of x equals 1. If g of x equals 1, it reduces to what? What would be the derivative of the product in the special case when g of x equals 1? Yeah, it'd just be f prime of x. And if f of x equals 1, what does it reduce to? G prime of x. So we know at the very least, it has to depend on f prime and g prime. But I could actually write that as f prime of x, g of x, and I could write this as f of x, g prime of x. As in this case, g of x is 1, and in the second case, f of x is 1. It's hard to know how to put in 1. Hard to see how to put in 1. But at the very least, we know it has to depend on f prime and g prime. How it depends on them, how it depends on, does f and g come into play as well? Not as clear. Okay. So now here's the first thought. We let n equal the space Oh no, let's not use N. Let's use P, the set of functions such that if f and g are in P, then fg prime is f prime g plus fg prime. So it's the set of functions such that if I take any two functions from that space, their product satisfies this conjectured product rule. So can somebody give me some examples of functions in P? Can you give me some elements in P? X. What else? We don't know x plus 1. Now, there is a gap. Now, maybe I'm just tired this morning, but there's a gap before x. What function might be able to be put there? We have x, x squared, x cubed. Yeah. We also know it works when we just take the function 1. Because if we take one of our functions to be 1, its derivative is just 0, the product rule is going to. So we know that this set of functions work. Okay? So here is a lot. Right, so if I take any two elements in P, the product rule will hold for their product. So we actually proved that if you take sine of x and cosine of x, the product rule holds for sine of x times cosine of x. But we don't know that the product rule holds for x times sine of x. So I haven't put sine and cosine into this. I know that sine of x times cosine of x, because I remember my trig, I know that it works. But I don't know that x times sine of x works. So I'm not putting sine and cosine in here. I'm just saying this is a space of functions where if I take any two functions in the space, the derivative of their product is f prime g plus fg prime. So here's my lemma. If f1 and f2 are in P, so is their sum. And by symmetry, it's symmetric in f and g. So instead of talking about things for f, I could talk about things for g. Is everybody okay with that? Symmetric doesn't matter if first or second product. Can you give me something related to the product rule where order does matter for the two functions? Quotient. So the quotient rule might be a lot harder to do here. But for the product rule, f and g and f, that should have the same derivative. So in fact, when we go back, should be symmetric if interchange f and g. Yeah. So we're trying to get a sense of what the answer is. I know what the answer is. I've proven the product rule more times than I can remember. What I want to talk about is how would you get there? How would you come up with an idea of what it should be? Okay, well, we talked about doing special cases and making it work there. All right, so now my claim is that if f1 and f2 are in this space, then so is their sum. More generally, A1 and A2 are any constants, then A1 F1 of x plus A2 F2 of x is in P, if F1, F2 are in P. This is a really nice result. So this is called a linear combination. Called a linear combination of F1 and F2. prove it. So consider f of x equals a1 f of x, f1x, plus a2 f2 of x. So what does f prime of x equal to? I'm sorry? Not a1 plus a2. F of x is a1 f1 of x plus a2 f2 of x. So what's the derivative of f of x? Try again. It starts off with a1. It's a1, almost, not a1 f prime of x. We have f of x is a1 f1 of x plus a2 f2 of x.
F1 prime of x.
F1 prime of x, right? Plus a2 f2 prime of x. So here we're just using, we know the derivative of a sum is the sum of the derivatives. I'm assuming I know that. The sum rule is much easier to prove than the product rule. And the sum rule is what you would want it to be. If you were to create laws of differentiation, you would definitely start with the derivative of a sum is the sum of derivatives. We're also using the constant rule. A constant times f, its derivative is the constant times the derivative. So used the sum rule, used the constant rule. Okay. Now, let's look at f of x times g of x. Let's take the derivative. This is a1 f1 of x plus a2 f2 of x times g of x prime. This is a1 f1 of x g of x plus a2 f2 of x g of x prime. What should I use to handle the derivative of that? What rule should I use now? Product rule and the sum rule. Well, we don't know the product rule.
Oh,
So what rule should we use first?
Sum.
Sum rule. So this is going to be a1 f1 of x g of x prime plus a2 f2 of x g of x prime. So this is just the sum rule. Now what do we use? First we used the sum rule. Now what do we use? So the onion, peel away. What's the next thing you can use? The constant rule. So then this would be a1 f1 of x g of x plus u prime plus a2 f2 of x g of x prime. And this is the constant rule. So is everybody comfortable with what we've done so far? So we have f of x, g of x prime is a1 f1x g of x prime plus a2 f2 of x g of x prime. But what do we know about f1x g of x prime? What are we assuming about f1 and f2? So can somebody tell me what we've assumed about f1 and f2? They're in P. So P is the set of all functions such that if you take any two things in P, the derivative of the product satisfies the conjectured product rule. So what do we know since f1 is in P and g is in P? What must be true about f1 times g? Oh, I'm not saying that it's in P. P is the set of functions such that if you take any two things in P, their product satisfies the conjectured product rule. The product rule works for F1 times G. So this means that this has to be A1 times F1 prime of X, G of X, plus F1 of X, G prime of X, plus A2, F2 prime of X, G of X, plus F2 of X, G prime of X. What are we doing? P is the set of all functions for which we know the product rule holds. So I'm saying, and we actually know that there are elements in P. We know P contains 1 and X squared and X cubed. So we know a lot of elements in P. We know the product rule holds for sine and cosine, but I don't know that it holds for X cubed times sine of X. So I'm not putting sine and cosine in here. So P is the set of functions such as if I take any two things from P, the product rule holds. Okay? We know what the product rule is whenever you choose two things from P. It turns out it's true when you choose any two functions that are differentiable. And so eventually, what are we going to show P is? P is the set of differentiable functions. Right now, we know P is the set of functions of the form 1x, x squared, x cubed. We're going to show that a lot more functions are in it. We're going to show if you take two functions in P, their sum is in P. More generally, any linear combination, I could take 5 times F1, and that's in P. Or I could take 5F1 plus 7F2. So now that I know this, if I know 1x, x squared, x cubed, I would know 3008 x cubed is in P. Or 3008 x cubed minus 17x to the 5th plus 11x minus 12 is in P. So we're going to see that P is much larger than we initially thought. And so at this point now, let's regroup things. Let's put all the G's together and all the G primes together. So this is going to be A1 F1 prime of X plus A2 F2 prime of X times G of X plus A1 F of X plus A2 F2 of X times G prime of X. What does this first factor equal? So what is the second factor? Which one is easier for you? What is A1 F1 of X plus A2 F2 of X equal? Let's go back a page. What is A1 F1 of X plus A2 F2 of X? It's just f of x. That's our function f of x. So I can replace this with an f of x over here. What about A1 F1 prime of x plus A2 F2 prime of x? Yeah, if you look at what we had a moment ago, that's just f prime of x. Oh, wait a minute. This is what we wanted to show. Low system resources, okay. Not quite sure why I have low system resources. So we just proved that if you take any two things in P, their linear combination is in P. So now we know a lot more. P contains any polynomial of finite degree. We can't take polynomials of infinite degree, but we can take polynomials of any finite degree. We just keep doing Lather-Rinse, repeat, Lather-Rinse, repeat, Lather-Rinse, repeat. So this is the shampoo math. Okay. Somebody in one of my classes said that the directions on shampoo is rinse, lather, repeat. I've always heard lather, rinse. As long as you keep repeating though, it doesn't matter. You're off by a verse 1. So it's not a huge deal. So shampoo mathematics. Let's say we have, 17x cubed minus 11x squared plus 8x plus 4. So we know 4x, x squared, and x cubed are in P. Right? Now we can multiply anything by a constant and it's still in P. So we now know 4, 8x, negative 11x squared, and 17x cubed are in P. Right? Everybody comfortable with that? This is just a special case where the second function is 0. Well, now we know 8x plus 4, negative 11x squared, 17x cubed are in P. I can just add the 8x and 4. Then I can add in the negative 11x squared and get negative 11x squared plus 8x plus 4, 17x cubed is in P. And then, once more into the breach, 17x cubed minus 11x squared plus 8x plus 4 is in P. So any finite sum of 1x, x squared is in P. So we've now proved the product rule for any finite sum. What would you like to do next? So we've proven the product rule holds for any finite sum. What would you like to do next? Infinite sums. And so I'm using this as my motivation for why we want to study infinite sums and convergence and all of this stuff. What is the motivation? The general idea in mathematics is prove something in a simple space and bootstrap up. So I'll put this in red. Start simple, prove, bootstrap up. So we were able to prove the product rule for finite polynomials just by knowing that it worked for 1x, x squared, x cubed, stuff like that. So this was a really nice result. So now the question is, what about infinite sums? We've seen, I think, one infinite sum already in this class. Does anybody remember the infinite sum we've seen? We did see that, yes. So one of the ones we saw was 1 minus the third plus the fifth minus the seventh. Yes. I want an infinite sum involving x, my mistake. An infinite sum involving x. I think we did that in this class. It's one of the standard functions. There's two definitions of this. One is an infinite sum, and the other comes through compound interest. Did we do e to the x in this class? And this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 is the sum and goes from 0 to infinity of x to the n over n factorial. Did we do this as the definition of e to the x? So this is an infinite sum. So whenever you have an infinite sum, the first question you always want to ask is, does it converge? What's the next question you ask? What does it converge to? Right? When you meet somebody on campus for the first time, there's a bunch of questions you ask, right? One of the questions you ask is not a question that I would ask when I was a college student. And the question might be, what's your cell phone number? Or sadly, what's your email address? In my freshman year, you had to physically go to a building and request an email address. And so the questions change a little bit. But the first question should still be, what's your name? Maybe where are you from is next. So do you converge? What do you converge to? There's a question you could ask after that. So we know it converges, we know what it converges to. What might you ask after that? We know it converges to a certain value. So you might ask, how quickly does it converge? How long is it going to take me to get to within a certain tolerance? how rapid is the convergence? So the questions are, does it converge? If yes, to what? And then the next is how fast? So these are the questions we want to answer. And this is where we need some notion of, what is a limit? How do you deal with an infinite sum? How do you prove convergence? All of this stuff. And one motivation is to try to replace complicated functions with simple functions. The big idea of Calc 1 is locally every function looks like a line. You can extend that. Instead of doing the best fit line, what could you do? Okay, well, what curve? What curve would you do after a line? So the tangent line is, I give you some function and you try to find the best fit straight line at the point. And that's the tangent line, and that's extremely valuable. What if you wanted to do better locally than the best fit tangent line? Instead of finding the best fit line, what would you try to find? Yeah, the best fit parabola. And so I can switch to green and then maybe try to find what's the best parabola nearby. And if the parabola wasn't enough for you, what would you go for next? Cubic. And so you just keep adding more and more degrees. And so if you look at what's going on, we have some numerical integration. So the first way to numerically integrate is the trapezoid rule. And what this basically says is, well, let's divide our interval from A to B into n equal pieces. So all the bases are going to be b minus a over n. We often said a equals 0 and b equals 1 just to make that easy, but each base has the same thickness. The area of a trapezoid is just 1/2 the sum of the two sides times the thickness. And if you think about that, why is this the case? Well, if I give you, two sides like this, I need to figure out what the area of the rectangle is plus the area of the triangle. The area of the triangle is 1/2 the area of that extra rectangle over here. So I'll leave it as a nice exercise for you to show that the area of a trapezoid is the thickness times the average of the two sides, the two parallel sides. And so this is a good way to try to find the area under the curve. We just chop it up into a lot of different points on the x-axis. Then we connect them and we form trapezoids. And for each one of these, we calculate the area, then we add it all up. And in the limit, as we take more and more points, this mesh is going to get finer and finer and finer, and it's going to converge to the area under the curve. So we've answered the first question. It converges. We've answered the second question. It converges to the area under the curve. And what's our third question? Sorry? How quickly? And so then what you want to do is you want to try to figure out what is the error in terms of how quickly it converges, how much are you off by? And the error is going to depend a little bit on how fast the function is oscillating. And it's going to depend also on the thickness of your points. So it makes sense that as your points get closer to each other, your error should get smaller. So the question is, at what scale? So let's say delta x is the difference between two adjacent points. Is the error proportional to delta x, or delta x squared, or delta x cubed, or delta x to the fourth? The higher the power of delta x, the better you're doing. Okay. The next one is Simpson's rule. Probably should put the slides in the opposite order, which is actually pretty easy to do. There you go. All right, so the next is Simpson's rule. And instead of using trapezoids, what it does now is it puts in an additional point in the middle, and it finds the best parabola it can going through those 3 points. So you've got to decide, how fair is this to compare? If I have to evaluate at the 2 endpoints and at the midpoint as well. So you want to make sure that you have the same number of computations, both Simpson's rule and the trapezoid. If I have my thickness be 1/100 for both of them, but I have all the middle points for Simpson's rule, well, Simpson's rule is using more points. And so it's not surprising if it does better than the trapezoid. So you want to make sure that you use the same number of points for both. And the idea is Simpson's rule actually will do a better job because it's using a parabola rather than a straight line. It's going to capture a little bit more in general. I'm not going to go into the details of the analysis. If anybody is interested, email me. I'm happy to either talk about it privately or do this in one of the application days. For a lot of things in life, we can't solve problems exactly. So we need to resort to numerical simulations. Is anybody here thinking of studying economics? Okay, yeah, give up hope of solving things exactly. You will be running simulation after simulation trying to estimate what things are. And you want to know how much is your error. How many of you have heard of the butterfly effect? Butterfly flaps its wings, it can cause a tsunami. One of my friends says we have to find this butterfly and stop it. This is a nice positive outlook on it. But the point of the butterfly effect is that there are a lot of things that are extremely sensitive to initial conditions. Did we have the little electron fractals in Newton's method yet? So we saw that if we change what we saw by a very small amount, we can change wildly what we converge to. And so there's a lot of sensitivity analysis that has to be done. One of my colleagues works on climate models, and he is not saying global warming is happening. He's not saying global warming is not happening. What he's saying is some of these models are extremely sensitive to very small changes in the parameters. And if you change some of the parameters ever so slightly, you get wildly different predictions for what's going to happen. And it means you've got to be extremely careful when you do these models. How many of you have seen a pendulum in physics or something swinging back and forth? I'm not going to actually use this pen because it's not very bad. I will use this mouse because it's not my computer. You're willing to get me a new mouse if necessary. Sorry, this is being recorded. I will replace the mouse if necessary. All right. So everybody agrees that if the mouse is hanging straight down, it's at rest. What if I move the mouse ever so slightly? What will happen? It'll just start swinging a little bit. Now imagine that this was an extremely strong, rigid rod over here. Not like this. Is there any other equilibrium point other than straight down? If this was perfectly rigid. Straight up would also be an equilibrium. What would happen if I tweak it and move it just a little bit from straight up? Yeah, now in fact here we can actually see massive swinging going on. Start breaking the computer. This is hard. So very small changes in initial condition at the bottom equilibrium really don't change things that much. Very small changes from the upper equilibrium very quickly lead to wildly different behavior as to where it is. You move it just a little bit down below, it still stays basically where it was. You move it just a little bit up top, and it's at a completely different place in a very short amount of time. These questions we're talking about, these series, these convergence issues, these are fundamental in all of science. And I'll be generous, I'll include economics and other disciplines like that in the conversation today. You want to know how well does something converge? You want to know how long it's going to take? You want to know how sensitive is it? When I'm trying to estimate the area, I want to know how quickly do I expect the convergence to be? Okay, I can approximate the area under the curve by using upper sums and lower sums. And I can use trapezoids or I can use parabolas. If I want to be within 1,000th of the true area, how many points do I need? It would be nice to know. And so you need to have some kind of understanding of rates of convergence so you can know when are you close enough. Okay, so this is hopefully motivating why we want to understand sequences and series and convergence. One idea was when we were just looking at the product rule, we could actually prove it for any finite polynomial. Another way we could have done it is we could have said, f of x is equal to an x to the n plus dot 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 plus a1x plus a0, g of x is equal to bm x to the m plus dot 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 plus b1x plus b0, and then look at f of x, g of x, and do the mess. And then do algebra, and then see that it is f prime of x, g of x, plus f of x, g prime of x. So if you want for extra credit, just do that. Just go through, do the algebra. It will work out. It's not horrible. But you can see that it's much better to break it up into simple things. If I can do it for two functions, I can do it for their linear combination. And so rather than having to do it for the general function, a n x to the n plus dot, 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 it's enough to just do it for x to the n and x to the n. So this is a key idea in mathematics. Break things down into something simple, understand, and then build up. Okay, so we want to talk about sequences that converge. So the most important is the geometric series. And so an is a0 times r to the n. And r is called the ratio. So we would have a0, a0r, a0r squared, dot, dot, dot. Often we take a0 equals 1, because if I multiply all of the terms by a0, I'm just rescaling everything by a constant. So consider Sn is 1 plus r squared plus r to the n. So this is the sum of the first n plus 1 terms of a geometric series. So there's a couple of ways to prove the geometric series formula. Later in the semester, I will bring in the basketball hoop and we'll play a game and prove the geometric series formula by doing a shootout. Right? But I want to do it at the same day as multivariable calculus because it's a pain in the ass to bring it all the way down here. So if we multiply by r, what's 1 times r? R. What's r times r? R squared. R to the n minus 2. R to the n minus 1 times r is r to the n, and r to the n times r is r to the n plus 1. What can we do to both sides? What should we do to these two equations? Subtract. And this is a telescoping sum. We saw this in the proof of the fundamental theorem of calculus. When we subtract, all the stuff in the middle is going to cancel. And that's the advantage of something like this. The r's cancel, the r squareds, all of these cancel. And we're left with Sn minus Rsn is 1 minus r to the n plus 1. Well, I can factor the left-hand side as 1 minus r times Sn. So we get that the finite geometric series 1 plus r to the n is 1 minus r to the n plus 1 over 1 minus r is 1 over 1 minus r to the n plus 1 over 1 minus r. And now what's nice is I can ask, what happens as n goes to infinity? Well, there are two terms on the right-hand side. There's the 1 over 1 minus r, and there's the r to the n plus 1 over 1 minus r. So as n goes to infinity, does the first factor 1 over 1 minus r, does that change at all? No. What about the second factor? What happens to that as n goes to infinity? And does the answer maybe depend on r? So no matter what r is it going to be, give me a value of r. Well, almost, you're extremely close. Negative 2 billion. Negative 2 billion is less than 1. So if I take negative 2 billion, negative 2 billion to the n plus 1 is going to be oscillating between plus and minus infinity. Well, you can do better than less than 1 and greater than 0. You're very close. It's not r that needs to be less than 1. It's something related to r that needs to be less than 1. The absolute value. So if the absolute value of r is less than 1, then let's call it S infinity, which is 1 plus r squared plus dot, 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 is just 1 over 1 minus r. And this is the geometric series formula. This is one of the most important formulas in mathematics. It allows us to evaluate an infinite sum exactly. One of the things that's really nice about a geometric series is if you only take finitely many terms and you look at what comes from that point onward, that's a geometric series as well. If I look at r to the 5th plus r to the 6th plus r to the 7th plus r to the 8th, let's just take a naught equals r to the 5th. So the tail of a geometric series is also a geometric series. We can evaluate a geometric series exactly. So for example, what's 1 plus a half plus a 4th plus an 8th plus a 16th? What would that equal? What is R for this? So what would R equal to this problem? One half. So R equals 1/2. The absolute value of R is less than 1. So this is just 1 over 1 minus R, which is 1 over 1 minus a half, which is just 2. I think we talked earlier about how this is reasonable. Here's 0, here's 2. The first step, I move half of the distance to 2. The next step, I move half of the remaining distance. I move to 1.5. The next step, I move half the distance remaining. Each step, I move half the distance remaining. Okay. So what we need now is, consider an infinite sum. The sum n goes from 0 to infinity of an. We want this to converge. It is necessary that the limit as n goes to infinity of an equals what if we want this series to converge? So if I want this to have a chance to converge, what must the terms be going to? 0. If the terms are oscillating, then my sum is going to oscillate depending on what I get. Eventually, if each term is not less than 1 billion, then I'm going to get a little boost by more than 1 billion. So does everybody agree that it is necessary that all the terms go to 0? If the terms don't go to 0, there's no way the sum can converge. So do you think it's sufficient? So can somebody give me an example of something in life that is necessary but not sufficient? Water. So water is necessary for survival, but it is not sufficient to just have water. If you don't have mathematics, you might be able to have your liquid needs fulfilled. No, you need food as well as another stuff like that. So there are many things in life that are necessary but not sufficient. So I will give you an example where it's not sufficient. Not a sufficient condition. There's lots of examples. This is my favorite. Anybody know what comes next? Okay, what comes next? What comes next? What comes next? Yep. How much time do I have to fill up? So it should be clear what the pattern is. The terms are clearly going to 0, but the sum is going to be as large as I want. So whenever you can, always try to find simple examples to show that something has issues. Okay. So we are now looking at your beautiful sequence. We see that it is unfortunately not enough that the terms go to 0. It's a necessary condition, but it's not a sufficient condition. So we need to start developing a whole slew of tests. When can we tell that a sequence will converge? So the first one, which is the simplest, is the alternating series test. Assume an goes from 0 to infinity, alternates sign term by term, and an is always greater than or equal to an plus 1. And the sum n goes from 0 to infinity of an converges. And let's think about what's going on. So let's say, we start with A1. And A1 brings us up to here. Then A2 brings us down some amount to A1 minus A2. Can it bring us down to something negative? Remember, each term can't be larger than the previous term in absolute value, and they alternate in sign. So the absolute value of A1 has to be greater than the absolute value of A2. So it can't bring me down to a negative number. I now add A3. What can you tell me about A3 relative to A2? It'll be less than that. So when I go up, can I go all the way back up to A1? So I go up some amount, and now I'm at A1 minus A2 plus A3. And now I go down. So I have A1 minus A2 plus A3 minus A4. And hopefully this is enough to show you what's going on. That when and in fact, we saw this with the example you mentioned earlier of pi over 4. 1 minus a third plus a fifth minus. That when it alternates like this, as you keep adding every two terms, after the initial red, every two terms is going to be a small negative that's going to pull me down a little bit. And I know I can't go down further than I was over here. So the question is just how much detail do we want to get into in the first class? I think this is enough detail to just see that it's going to have to converge. This is not a fully rigorous proof. To me, this is close enough, especially with spring break so quickly approaching. All right, so this is a good place to stop, and we will continue with sequences and series later. But again, the motivation for a lot of what we did today is to see, for a lot of things, we could prove things for finite sums. If we can understand what goes on in the limit, we actually have results. We now have to understand these infinite sums. All right.